This video is the first in a set and provides an overview of primary control functions and an in-depth presentation of thermomechanical primary controls, commonly referred to as stack relays. It is intended to serve as a review for experienced service technicians and as part of an instructor-supervised session for students participating in an oil heat training program. We'll start by discussing oil heat and electricity. Oil heat systems require electricity to operate.
In a typical system, line voltage flows in a series circuit from the fuse or circuit breaker to a remote toggle switch located away from the heating unit. From there, it continues to a service switch at the oil-fired appliance, next to the limit controls, and then to the primary control, which distributes power to the oil burner components to manage the combustion process. Working on an oil heat system often requires that you perform tasks related to the various electrical switches and controls incorporated into the system. It is imperative that you fully understand each of the components you work on, that you always follow governing codes and ordinances, and that you abide by safe work practices at all times. Because it has become such an integral part of our daily lives, we tend to forget that electricity can be hazardous. Before attempting to service electrical components, take a few moments to be certain that you understand the dangers involved and follow all the correct safety procedures. When working with electricity, you should always avoid working in wet areas and utilize protective equipment if working in areas which may become wet. Inspect power tools and equipment prior to use. Use insulated tools and double-check to ensure that the insulation isn't compromised. Use the correct size UL-approved extension cords. Make sure that the equipment being serviced and any electrical tools being used are properly grounded. Never use a 2-prong ungrounded adapter with a 3-prong appliance or extension cord. Avoid overloading circuits. Whenever possible, de-energize equipment before servicing. Remember that switches can fail. Always test de-energized circuits before commencing work. Lockout involves applying a physical lock to the power source of circuits and equipment after they've been shut off and de-energized. Then tag out the circuit with an easy-to-see sign or label that lets everyone know that you're working on the circuit. Since equipment lockout often isn't practical, OSHA considers shutting off the equipment in 2 places as the equivalent of lockout. For example, tag out without a lockout will be adequate if the equipment is shut off and tagged at both the breaker and at the unit. Remember, while tag out might take a few extra moments, it's worth the effort to prevent someone from accidentally energizing a circuit while you're working on it. In this video, when we say turn off the electrical supply, we're referring to lockout tagout.
Now we'll introduce you to primary controls.
The safe, automatic operation of the combustion function of an oil heat system is dependent on the interaction between the thermostat, which opens and closes a circuit based on temperature changes in the heated space, the limit control, which opens and closes a circuit based on temperature or pressure changes in the system, and the primary control, which regulates the operation of the oil burner. In a properly designed, installed, and serviced system, these 3 components work together to safely satisfy a call for space heating, cooling, or water heating. The primary control, often referred to as the heart of the oil heat control system, has 3 main functions: to respond to the thermostat, to control the startup, run cycle, and shutdown of the oil burner, and to respond to the limit control if necessary. While primary controls have evolved from relatively simple stack switches to modern microprocessor-based devices, the basic principles of their operation have remained the same. The primary control accomplishes its mission by reacting to the presence or absence of flame through thermal or visual means, managing burner startup by checking for a flame before powering ignition transformers or igniters and energizing burner motors and oil valves, supervising burner shutdown once the thermostat is satisfied or the limit control opens. All primary controls have 120-volt AC line voltage circuits. In a heating system, line voltage is supplied to the primary control through the limit control when the temperature in a water heater, boiler, or furnace, or the pressure in a steam boiler is below the limit setting. Once the limit control is satisfied, it breaks or opens the circuit, de-energizing the primary control and shutting down the burner. Most primary controls also have 24-volt AC low-voltage circuits to accommodate thermostats and/or other devices. The low-voltage circuit is closed when the thermostat senses the need for an increase in room temperature. When the thermostat is satisfied, it opens the circuit. In steam boiler applications, the thermostat is connected directly to the primary control. In warm air applications, the thermostat may be connected to a separate furnace control board or directly to the primary control. In hydronic or hot water systems, the thermostat is commonly connected to an aquastat or a switching relay. For the primary control to activate the oil burner, both the line and low voltage circuits must be closed. In most cases, that means that if either the thermostat or the limit control is satisfied or open, the primary control will not activate the oil burner. In systems with a line voltage thermostat or with a low voltage thermostat connected to controls other than the primary control, a jumper is normally placed between the primary's thermostat terminals, permanently closing the low voltage circuit. The primary control is then activated solely by the limit control. Some systems have an additional control wired in parallel with the thermostat. In those cases, the primary's low voltage circuit can be completed through either the thermostat or that additional control. For example, a steam boiler with a domestic hot water coil installed normally has an aquastat wired to the low voltage terminals. This enables the boiler to maintain domestic hot water even when the thermostat is not calling for heat.
Primary controls detect both the presence and absence of flame.
A safety feature of primary controls is they will not activate the burner for startup if the control senses a flame during the off cycle. This prevents additional oil from being pumped into a unit that already has a fire burning before startup. It is also critically important that primary controls react quickly to the presence or absence of flame while the oil burner is running. The primary control must shut the burner off promptly if no flame is established on startup, or if the flame is lost during the run cycle. If the primary control did not shut off the oil burner in these circumstances, the burner could continue to pump fuel into the unit, creating hazardous conditions. When the primary control shuts off the burner because no flame is sensed, this condition is referred to as being off on safety, in safety, or in lockout. Once the primary control goes off on safety, it must be manually reset before it can send power to the burner again. The amount of the time that elapses from the start of a cycle in which flame is not established until the control goes off on safety is referred to as the safety timing. Slight variations from an individual control's stated safety timing often exist due to manufacturing tolerances, voltage variations, and temperature changes. It's important to understand that power outages do not affect flame detection. If power is lost during a running cycle, the control will not go off on safety, and it will normally re-energize the burner after power is restored.
Oil heat systems operate in one of two ignition modes: intermittent duty or interrupted duty.
Intermittent duty ignition means that the spark across the electrodes that ignites the oil is present throughout the entire time the burner is running. Interrupted duty ignition means the spark comes on for a short time at the beginning of each burner operating cycle and is turned off once flame is established. Interrupted duty ignition is much better because it makes for quieter combustion, lowers NOx emissions, and increases the life of the ignition system. Primary controls can be designated either interrupted duty or intermittent duty. Primary controls that allow for interrupted duty ignition can be adapted for intermittent duty ignition, but primary controls designed for intermittent ignition cannot be used for interrupted ignition. Through a confusing evolution of terminology, what we now call intermittent was formerly called constant duty ignition, and what we now call interrupted was formerly called intermittent duty. It's important that you understand these differences because you may encounter primary controls in the field which are labeled according to the old system, and may even receive replacement controls from older stock which use the old nomenclature.
To review, with intermittent ignition, the spark is on for the entire time the burner is running. With interrupted ignition, the spark comes on at the beginning of each cycle and goes off after flame is established. The term constant ignition is no longer used with oil heat systems. It is used with gas systems that have a pilot light that's always on, regardless of whether or not the burner is operating.
There are two basic types of primary controls commonly found in the field today: thermomechanical primary controls and CAD cell primary controls.
Thermomechanical primary controls.
Thermomechanical controls, commonly called stack switches or stack relays, utilize bimetals to detect flame and to mechanically open and close electrical contacts to provide burner control. They have spring-loaded reset buttons and a thermal safety switch that must cool before allowing the control to be removed from lockout. Through the 1960s, such stack switches were the industry's standard primary control. Unfortunately, there are too many of these antiques still operating in our customers' homes today. Oil heat technology has advanced greatly in the years since stack switches were the state of the art. Modern oil heat systems operate cleaner, more efficiently, and much more economically than systems designed when these controls were the standard. We'd all be doing our customers a great service by recommending equipment upgrades on any system still operating with a stack-mounted primary control. There are many brands and types of these controls in the field. Some operate on line voltage only with no low-voltage circuit. There are mercury tube controls, two-piece controls, and a host of controls manufactured by companies that many of us have never heard of. Luckily, the major suppliers of thermomechanical primary controls adopted similar standards, so basic wiring is the same, regardless of the make and model. Mounting instructions are also similar for all stack relays, except those containing mercury tubes, which must be mounted level. Some of the older designs provided intermittent duty ignition. Again, this is the ignition method in which the spark is present for the entire time the burner is firing. And there are older interrupted duty ignition primary controls where the spark comes on only to light the flame. For the next few minutes, we'll examine the most commonly found thermomechanical primary controls still in operation today, the Honeywell RA 117A. The RA 117A is typically mounted in the flue pipe, although you may occasionally find one mounted directly into the flue collector or elsewhere on the heating unit.
The RA 117A employs a bimetal heat-sensing element for flame detection.
This heat-sensing element must be in the path of the combustion gases between the heating unit and the draft regulator. It should be centered in the flue pipe at a point where it will be exposed to flue gases between 300 and 1000 degrees Fahrenheit. When the burner operates, heat rises and passes over the bimetal element, which expands. This forces motion in a drive shaft which closes contacts that enable the burner to continue operating. If the bimetal is not sufficiently heated, a built-in safety switch shuts off the burner in approximately 75 seconds. It cannot be started again until the safety switch is manually reset. If the flame is lost during the run cycle, the RA 117A shuts the system down for approximately 1 minute and makes one attempt to restart. If the flame is re-established, the system will continue to operate normally. If the flame is not re-established, the system shuts off on safety. Some stack-mounted primary controls do not make the attempt to restart. They simply shut off on safety when flame is lost during the run cycle.
Wiring of oil heat systems must always comply with all applicable codes and regulations, be completed in accordance with manufacturer's instructions, and be performed by a qualified technician.
The power or hot lead from the limit control is connected to terminal 1. All neutrals are connected to terminal 2. One wire from the burner motor and one from the oil valve, if used, are connected to terminal 3. And if the unit operates on interrupted duty ignition, one wire from the transformer is connected to terminal 4. For intermittent duty ignition, connect the transformer lead to terminal 3, along with the burner motor lead, leaving terminal 4 empty. If the control has a green terminal, it should be connected to ground. Remember, each component, the burner motor, transformer, and optional oil valve, has 2 wires. One wire from each connects to the neutral, terminal 2. The low voltage side of this primary control has 3 terminals, R, W, and B. If the system has a 2-wire thermostat, it is connected to the W and B terminals. If a 3-wire heat-only thermostat is used, connect the red wire to terminal R, white wire to W, and black wire to B. If there are no low-voltage devices connected to the primary control, a jumper is placed between the W and B terminals. Some models only have 2 low-voltage terminals for the thermostat connection, normally labeled TT.
For the next few minutes, we'll examine the operation of the RA117A.
If all components are functioning properly, the control is in standby mode until line voltage is applied through the limit control to terminal 1, and a call for heat from the thermostat completes the circuit between W and B, or TT. Then terminal 4 will be powered, and terminal 3 will be powered a split second later. The transformer will generate ignition through the electrodes. The motor will turn the fuel pump and burner fan. If there's a delayed oil valve installed, it will open based on its delay timing. Once flame is established and heated flue gases pass over and expand the bimetal detector element, the safety switch heater will be de-energized, preventing the unit from shutting off on safety. The ignition circuit will be de-energized, shutting off the transformer if the unit operates on interrupted ignition. The oil burner will then continue to run until either the thermostat is satisfied, opening the low voltage circuit, or the limit control is satisfied, opening the line voltage circuit. Either of these actions causes the primary control to cut power to terminals 3 and 4, safely shutting down the oil burner. The primary control then returns to standby mode.
It's important to check the safety timing of primary controls every time you perform a service call.
Note the timing on your service invoice. To check the safety timing, turn off the electrical supply. Either block the flow of oil by installing your pressure gauge in the nozzle port, or remove the stack switch from the flue pipe. Turn on the electrical supply. Make sure that both the line and low voltage circuits are complete. The control should energize and shut off on safety in approximately 75 seconds. If it checks out, clean the bimetal before reinstalling it. If the control does not go off on safety within 120 seconds, replace it and be sure to check the timing on the new control. Some service technicians make it a habit to put these stack switches off on safety as an extra precaution to keep the unit from starting while they're performing maintenance on the oil burner. Some models have a push lever to do this manually. Simply push the trip lever and the reset button pops out. Note that tripping the reset button shuts down power to the burner but does not disconnect the power supply. To avoid electrical shock, turn off the electrical supply.
Professional service technicians understand that accurate troubleshooting requires the proper tools.
In addition to a complete set of hand tools, oil heat service technicians should carry and use appropriate test equipment, including an efficiency kit, vacuum and pressure gauges, insulated jumper wires, a voltmeter, an ohm meter, and an amp probe. The proper use of this equipment simplifies troubleshooting and eliminates guesswork. Let's use the example of an oil burner that won't start. Normally, an experienced service technician will first ask the customer about the situation and listen closely to their responses. Be sure to ask if they've pressed the reset button and advise them that it should never be pressed more than once. Then verify that electrical switches are in the on position and that the thermostat is set above room temperature. Check to be sure that there is not a fire burning in the chamber. Now you're ready to check the primary control. Remove the cover and visually check the spring-loaded reset to see if the unit has shut off on safety. If the primary control is not off on safety, check for the proper voltage between terminals 1 and 2. If there is no reading on your meter, leave one probe of your meter on terminal 1 and touch the other probe of your meter to a copper water pipe. If you now have a reading on your meter, the trouble is in the neutral leg. Check for a broken neutral back through the system. If there's no voltage even when you touch the probe to the water pipe, check for power at the limit controls, the switch, and the fuse or circuit breaker. If there is sufficient voltage, verify that the unit is in step, meaning that the contacts affected by the bimetal heat sensing element are properly aligned. This control is put in step by pulling the drive shaft lever forward 1/4 inch and slowly releasing it. If the primary still doesn't operate, the problem may be in the low voltage circuit. After removing all low voltage wiring from the control to avoid harming today's computerized thermostats, place a jumper across the thermostat terminals, either the TT terminals or the WNB terminals. If the primary control then starts the burner, the problem is in the low voltage circuit. If the primary is off on safety, check the combustion chamber. If it contains excess oil, follow your company's procedures to eliminate the oil. Never attempt to fire an oil burner into a chamber saturated with oil. If the chamber is free of excess oil, press the reset button. If the relay energizes but the burner motor doesn't spin, turn off the electrical supply and check the electrical connections and the burner motor. If the burner runs and shuts off on safety, check the bimetal sensor. It may be coated with soot, which prevents it from sensing the temperature in the flue. Clean the bimetal and continue your troubleshooting to find out why the unit is sooting. If the burner starts and continues to run normally after you push the reset button, your job still isn't over. Simply pressing the reset button is not solving the problem. You must find the reason why the unit went off on safety and take action to keep it from happening again.
Remember, keeping outdated technology limping along in an attempt to save your customer money isn't really saving them anything in the long run. If the unit is old enough to still have a thermomechanical primary control, it's probably time to recommend new, high-efficiency oil heat equipment that will operate cleaner and more efficiently. An investment in a new, state-of-the-art oil heat system will provide greater comfort and lower fuel bills for years to come.